And just like the parabola, these equations also generate the ellipse, and it depends on the eccentricity here. And for the parabola, the eccentricity is 1. And so this number, eccentricity here, if it's less than 1, if it's between 0 and 1, and then we will get an ellipse. And so just like in the case of the parabola, the reason we have 4 of them is because it depends on where the directrix is, whether it's to the right, to the left of the parabola, or is it below, or is it above. And then we'll look at some examples, and that'll become clear. And so here we have we have an ellipse, and this directrix right here is the line x equal to negative 8. And so let's look at one where it's negative 10 first. So this directrix is x equal to negative 10. And again, the ellipse has 2 foci. One of them has to be at the focus, must be at the pole. So one of the 2 foci of the ellipse must be at the pole. And for this particular ellipse, the directrix is the line x equal to negative 10. And here we chose an eccentricity of 0.6. And what that means is this. The distance from the point to the focus dividing by the distance from point to directrix must equal to 0.6. So we take this point, then this distance point to focus dividing by distance point to directrix must equal to 0.6. And same thing here, if we take this point, then the distance from the point to the focus dividing by the distance from the point to the directrix must be 0.6. And so that's how the points on the ellipse are generated, is that if a point is on the ellipse, then the distance from point to focus dividing by distance from point to directrix must be the eccentricity of 0.6. And the equation for this ellipse would be the 0.6 times 10 for the directrix, and then 1 minus eccentricity times cosine of theta. And now let's vary the directrix, and so we can see the how the shape of the ellipse also varies. Here's eccentricity, x equal to negative 9, x equal to negative 8, x equal to negative 7, x equal to negative 6. Once again, this number is the eccentricity. This number comes from the directrix, and we take the absolute value. This is directrix x equal to negative 5, and so we get a 5 here. This is directrix x equal to negative 4, so we get a 4 here. Directrix x equal to negative 3, x equal to negative 2, x equal to negative 1. And then we can also have the type of ellipse where the directrix is to the right of the focus. So the directrix can be to the left of the focus, to the right of the focus, or the pole. Or it could be above the pole, or it could be below the pole. And so in this case we have the directrix is x equal to 10. And so the equation will be eccentricity is 0.6 times 10 divided by 1 plus eccentricity times cosine of theta. If the directrix is to the left of the pole, then it would have been 1 minus. But if it's to the right, it'd be 1 plus the cosine, the eccentricity times the cosine. And now let's look at the directrix x equal to 9, x equal to 8, x equal to 7, directrix x equal to 6, x equal to 5, x equal to 4, x equal to 3, and 1. So And then we could also have the type where the directrix is below the pole. And again, to generate the points on the ellipse, the distance from the point to the focus or to the pole, dividing by distance from point to directrix, must be equal to the eccentricity of 0.6. And obviously, if we change the eccentricity number, then we get a different ellipse. As though the 0.6, that's for the eccentricity, and then we take the absolute value of this negative 10, which is 10. And here's negative 9. The eccentricity is y equal to negative 9, negative 8, negative 7, y equal to negative 6, y equal to negative 4, 5, and here's y equal to negative 4, negative 3, negative 2, and negative 1. And here we have the type where the directrix is above the pole. So here we have the directrix y equal to 10. And we're also using eccentricity of 0.6. So the equation would be 0.6 times 10 divided by 1 plus 0.6 times sine of theta. So here's eccentricity directrix y equal to 9. Directrix y equal to 8, y equal to 7, y equal to 6, y equal to 5, y equal to 4, y equal to 3, 2, and 1. And here's the summary of what we just did. So if the directrix is below the pole, then we get this type of equation. It'd be 1, the bottom will be 1 minus eccentricity times sine of theta. If the directrix is above the pole or the foci, if it's above, then we have the equation of the type 1 plus eccentricity times sine of theta. If the directrix is to the left of the pole or to the left of the foci, then we get the equation that has denominator 1 minus eccentricity times cosine of theta. And then the last case is where the directrix is to the right of the pole or of the foci. Then we have the type that's 1, the denominator is 1 plus eccentricity times the cosine of theta.